So my final presentation of today, nonlinear analysis with examples. So in this presentation, I'm going to talk about nonlinear analysis, a little bit of the theory involved in the nonlinear analysis and how to do it in opensees. I've showed you briefly in the last presentation this morning how to do some simple nonlinear analysis. This presentation is more sort of in-depth of the different options available and what they do. I kind of glossed over them this morning. And I'll spend a great deal of time on basically the transient integrators, the different options, what stability means in a nonlinear analysis setting, what do we do with this energy dissipation, how we conserve momentum and stuff like that that you don't really think about when you do nonlinear analysis. We'll talk about it briefly. We'll show stuff of how you can play around, what sort of things you can do in openseas you really can't do in the other applications. But it's something that it should really get you thinking. Linear analysis it's pretty standard and straightforward. When you get to nonlinear analysis, it's really opening up a whole kettle of worms that nobody really thinks about when they do their nonlinear analysis. And I'm just hoping to sort of get you thinking about it today. So again, the outline of what I want to talk about is why do we do nonlinear analysis? Basically, the openseas options and the transient integration schemes. So the first thing, geometric nonlinearities basically occur when a load's big enough to impose a large displacement or a large strain or a combination of both. We can also have material nonlinearities, like the materials that we build our buildings with, steel and concrete. They are nonlinear. So when you get up to the nonlinear range, you do have to do nonlinear analysis. And finally, when we have contact problems, two buildings pounding against each other, as you'll see tomorrow with in the soils moving around the pile during an earthquake, there's all contact involved. When that's involved, we have to go again to nonlinear analysis. Nonlinear analysis is much harder than linear analysis. It takes a great deal more thought when you're setting up your model, how to capture all the nonlinearities. Where is the problems going to occur? Are we worried about the beam to column connection? How do we model that connection properly? It's not just like putting in two elements. We really have to think about how we're going to do the modeling. How we model has a great impact on what the results are going to be. I could show you blind prediction contests, single columns, and just basically people picking slightly different input parameters. The results were varied quite widely. So it's really important when you're creating your nonlinear model to think about these things. And typically, students starting off are just going to see two beam columns and they're going to connect them. There's a lot more thought you have to do. Desmond's going to talk a little bit about it tomorrow. That takes a lot more computational time. When you do nonlinear analysis, we're doing Newton-Raphson iterations. We're doing 10 steps, say, per iteration. So things take a lot longer to run. It does not always converge. You will not always get a solution for your model, depending on what your input model was and how you did the nonlinear analysis. You are not guaranteed that it's always going to work. And it will, even though it does converge, you are not guaranteed that it's the correct solution that it's converged to. You will get answers. When you get answers from nonlinear analysis, always go in and check the answers. Do they make sense? Professor Mahan is not here today. He gets money consulting, just going around looking at people's, looking at the models, seeing what the output, and he knows if they make sense or not. It's a skill you need to develop as these graduate students. But you really have to look at these results and ask yourselves, do they make sense? Simulation platforms, openseas, Abacus, they will all give you answers. It's up to you to make sense of, do these make sense? Are these realistic answers? Because as I say, the computer is going to give you numbers. That's all they might be, is numbers. They might have no actual, they might be totally inaccurate. And it's something you're going to have to learn to figure out for yourselves. Okay? So even though nonlinear is much harder, requires more time, it's not always right. Typically, we have to do nonlinear analysis. So we have to do it. The first thing we do is we check our model. Okay? That is the most important thing to do. That is the greatest source of the problems in your model, or in the analysis, is actually going to be in the model you create. So that is where you need to spend an awful lot of time, is checking that model, making sure it makes sense, making sure it captures everything you think is going to happen in this structure. So opensees, the analysis options. As I say, we've got constraint handlers, numbers, convergence tests, solution algorithms, integrators, and system of equations. So what I'm going to do next is I'm going to talk about sort of each command individually and the different options and what they actually mean. So the first and simplest one to explain is the convergence test. There are three basic ones. We want to have a look at the norm of the imbalance, the norm of the displacement increment, and the norm of the energy increment. Now in all these convergence tests, it's actually looking at the system of equations, that AX equals B matrix. It does not actually go to the nodes or go to the elements and ask for energy. It doesn't go to the nodes and ask for nodal displacements. It just goes to that system of equation and asks for either the x vector or the b vector. So what those actual norms mean, like typically they are the norm of the imbalance, the norm of the displacement increment, but they're not always that. Okay? It all depends on what x and b is, and that all depends on what integration scheme you've specified and how you're enforcing the constraints. We'll talk a little bit about the constraint, how that affects the matrix later on. But those have those basically say what's actually in those x and b vectors. And it's those x and b vectors that we're using in our convergence test. Okay? So the command test norm imbalance is just doing the norm of the r, whatever is the AX equals B with the r, that typically that's the resisting force, the unbalance. The norm displacement increment is just looking at the norm of the U transpose U. U is typically the displacement increment at every step, though not necessarily all the time. And the norm of the energy increment is just looking at the U transpose R. Okay? So again, they're just looking at what's in the system of equation, the AX equals B. What's in that system of equation depends on what the convergence test is and what your integration scheme is. Other tests are what are called the relative tests. So the test, just a relative in front of those names. So the first time it will use that as your first convergence criteria, and then subsequent iterations are compared to the first to see if it's converged or not. Okay, so the first one is always going to fail, and it's going to use that norm from the first one as the criteria for converging. Everybody understand the relatives? Okay. Okay, the next command is the numbering scheme. There's a mapping between the degrees of freedom at nodes and the matrix equations, the AX equals B. So how does, where things go in that matrix equation, AX equals B, depends on the numbering scheme. So the number just does this mapping for you. There are three available in opensees: the plain number, reverse cutting McKenna, and AMD. And unless you're using, so the plain number could be used for when using a sparse solver. Just use the plain number because the sparse solver does its own numbering scheme anyway. So it'll take whatever numbering scheme I give it and say, we don't like what you did. We do a lot better job. So we're just going to ignore the mapping you've given us. So they do their own. So use the plain when you're using a sparse solver. The other two, reverse cutting McKenna and AMD, they're when you're using one of the bandit or the profile solvers. So I typically use reverse cutting McKenna. It seems to always work the best for me when I'm using either the profile or a bandit solver. Okay? So as I say, it just does the mapping. AMD is something I was told to implement by a computer science professor up on campus, but I haven't found a situation where I'm getting a better performance when I use that numbering scheme. Okay, the solution algorithms. If we have a linear elastic problem, or if we're using a explicit time integration scheme, the solution algorithm we want to use is linear. The linear solution algorithm, I'm showing actually the code that's implemented on the right. If you actually go look at the code, because of our, say, our modular design and how we've set up the system, that's the basic code you'll see in opensees. So all we're going to do is we're going to form the imbalance. We're going to tell the integrator to form the imbalance. We're going to tell the integrator to form the tangent. We're going to solve. We're going to solve that AX equals B. And then we're going to tell the integrator to update the nodal displacements based on what the x vector is in the system of equation. Okay? So that's the linear solution algorithm. That's what it does, and that's what the code looks like in opensees. That's kind of the advantage of this modular design, is that's how simple we can actually make the linear solution algorithm. The next option is the Newton algorithm. This is the bread and butter for the nonlinear analysis. It's the one most people use. And this here on the right again is the code. Again, it's incredibly simple when you break it all up into the components that we have. So the first thing we do is we form the imbalance, and then until we've achieved convergence, we form the tangent, we solve, and we get the integrator to update, and then we form the imbalance again. Okay? So that's what the actual code looks like in the, if you go look at the source code. And the command is algorithm Newton. The next command is this modified Newton. This is typically the first thing people go to when their Newton algorithm fails. As you see, we have this dash initial option, and that's the option most people will start using. But basically, what modified Newton does over regular Newton is this form tangent here, that's taken outside the do loop. So the integrator forms it unbalanced, and the integrator forms the tangent. That's all up here, and then the rest of the do loop stays the same. Okay? So that's the only difference between regular Newton and modified Newton. We just form the tangent outside the do loop. So the tangent is formed once. And if we're using an initial option, the tangent is formed with this initial flag, so that it tells the elements to give them back their initial tangent. So I'm just showing here what's sort of the convergence between a regular Newton algorithm and a modified Newton algorithm. With regular Newton, you should converge faster than the modified Newton. I say the regular Newton is using the current tangent at every solution step to get to the solution. So hopefully we'll get there in 4. The modified Newton is using that initial tangent at the start of the step. So this slope here stays the same at every step. So you see it's taken more iterations to get there. So see, for a nice system like this, where the solution path is nice and curved and there's no kinks or things, Newton will always converge a lot faster. The problem is, for our models, when they start going nonlinear, we don't have a nice smooth surface on which we're looking for our solution. Somebody once talked about it as like the most desolate sort of canyon kind of thing you could think of, where you've got crags and valleys and things, there's just craggy mountain kind of surface that you're trying to find a solution on, where every time you hit, you got all these kinks and you just don't know where to go. That's kind of the solution that that's our solution space. We don't have this nice solution space. That's why we have problems when we're trying to converge. So Newton works nice if your system is nicely behaved. But when it starts getting kinks and all this kind of stuff, we have to switch to modified Newton. And there are a lot of other options in there. I'm not going to talk about them too much. Pretty much Newton and the modified Newton with the initial are pretty much all we're going to talk about here. but we have some line search algorithms inside the code, which actually turn up a lot in the Stanford scripts. And there are also some accelerated methods as well. Those constraints are important because these affect how those constraints, the multi-point constraints, are actually handled in the matrix equation. So basically, if you go to a textbook, there's many ways to write that matrix equation for the multi-point constraints. Basically, how two nodes are going to move together. So I've pretty much put all the different ways of these are all the same matrix equation, just expressed a little differently. So if we're dealing with the transformation, so if you specify your handler as transformation, this is the matrix equation we're solving when we solve AX equals B. As you see, the K is T transpose KT, and the R vector is T transpose R, where T is this matrix here. Okay? So we do a transformation on that matrix before we put it into the global system. So if we specify constraints as Lagrange, this is actually the matrix equation that's set up. As you see, the original K system matrix is the same, but what we get are our constraint matrix appear on the off diagonals. This constraint matrix here, C, they appear on the off diagonals. We get a 0 on this diagonal here. So we're solving basically a slightly different system. You'll note that if you're using norm of the displacement increment, you're not just solving for the displacement increments, you're also solving for some lambdas in there. Those lambdas are basically equivalent to the penalty in the penalty method to enforce that constraint. Those values turn out to be the same. So this is actually the equation you're solving when you use Lagrange. And then if you're using the penalty method, AX equals B is basically the original structural matrix augmented with this C transpose alpha C, where this alpha is our penalty factors that you specify in the command. And then the right-hand side has also got some forces, but these are typically equal to 0 because that Q matrix is typically equal to 0 for our systems. So we're basically dealing with this. So the difference between the transformations is the penalty method is nice because it keeps the sparsity of our structural matrix. So if we got a really tall building and we got constraints in there, it doesn't mess up the sparsity pattern of our matrix. We like to keep it nice. When we start dealing with the transformation matrix and we start dealing with all the transformations, this is typically a smaller matrix, but it's typically a much denser matrix. And when you go to solving AX equals B for very large systems, the time to solve a very dense matrix takes a lot longer to solve even a larger matrix that is a lot more sparse. Okay? So sometimes it's just beneficial, even though the system is larger, to stick with the penalty method. Okay? The only things that are going on is the penalty method, like it does introduce others. It's kind of like introducing really stiff elements into your system. So it introduces, the modes they're slightly changed from the original system. That's a disadvantage of the penalty method. So does everybody kind of see these different equations, understand them? Okay. Okay, for the system, AX equals B. For small problems, it doesn't really matter what system you use. Unless you've got as we saw this morning, profile SPD, band SPD, and sparse SPD, they all assume the matrix is sparse, positive, definite. So if we had, like this morning when we had that problem where the matrix goes negative definite, these solvers will not work for those models, in which case we must stick with one of the general solvers. The disadvantage of a general solver is that it takes twice as long to solve as the profiles, as the symmetric positive definite solver for the small models. Now when we go to really, really large systems, okay, I'm going to take everybody's name who's here today just to make sure I don't get this coming back from you. When you go to a really, really large system, the only type of solver you should ever use are these sparse solvers down at the bottom, okay? There is another one which Pedro Aldrino will probably talk about tomorrow called MUMPS, which is not in the sequential version of opensees. But it's another option, and he highly recommends it, that you can use, and it will be in the sequential version shortly. But never, ever, ever, for a large model, do I ever want to see in your script one of these other solvers, okay? Because you can go from spending days analyzing your problems to hours just by choosing the appropriate solver. And for a large model, anything over, even over 1,000 degrees of freedom, you're going to really start noticing the difference when you're doing all these matrix equations, just by switching to a sparse solver. Now I get emails from people who've been to my workshops and who send me crap with these, profile SPD still in their script. Okay? I don't want to see any more of it. It's got to be sparse. Okay? These ones are nice for checking, is this, at the start, because some of these sparse solvers will actually give you a solution when your model is when it's negative definite, or even sort of round off when there should be when you got some rigid modes in your thing that you haven't taken care of, you haven't got enough, your fixity condition isn't right. Some of these solvers will actually work. They'll actually give you an answer just because, as I say, because of what's going on in the hardware with the numerical computations, whereas these solvers will typically fail. But large models always use a sparse solver. Question?
What's wrong with using sparse matrix for a small model?
Other than the fact that it mightn't always pick up the fact that there's a problem in your model. For example, you don't have enough boundary conditions, or you've specified a material with a zero tangent kind of thing. Some of these solvers will actually give you a solution to that. But that's their only, right, yeah.
So I just want to know whether you have a better quantitative definition of a large system.
Okay, well it's not just, the large systems, see, it's not just the size, the number of degrees of freedom. It's also how they're connected, okay? I can come with a really tall, slender building, in which case you could get away with a much larger n than I had if I was just modeling a cube. Okay, the n, when you go from one to another, it's kind of model dependent. Okay, so these sparse, when you get this really big thing, these sparse solvers are die, whereas this profile or a banded general will just fly through that, to solving that matrix equation.
So if it doesn't converge, we just try this one.
Well, if it starts, I run the analysis, and if the model's not done in a minute or two, I go, this is taking me too long. Okay, and then I start thinking, okay, let me change the solver or something. So if it's not, it's basically my patience. So that's kind of when I judge it. But as I say, you can go from days to hours just by picking the appropriate solver. So when you got models that are running for hours, run it once time step, then just play with different solvers to find the solver that's going to work best. Okay?
Is it possible, for example, for earthquake excitation, for the first couple of seconds, we use the simple one, and
right.
beyond a certain point, we use the other?
Well, what I don't, what you could do in your script is you could do one step with each one, time it. You have a little for each, do one step with each one for a couple of steps, and then time it and say, okay, well, this one was the quickest one, and then use that for the rest of the analysis. That would work. I haven't actually done that. I should do that, but I haven't. Okay, next we come to the integration integrator command. Two types of integrators in opensees: static integrators, transient integrators. Basically, the transient integrators are solving a nonlinear equation of this form, and the static integrators are this form. This one you mightn't have seen before. So basically what we're trying to determine is the u and the lambdas that satisfy this equation here. Okay? The transient analysis is pretty simple. We're trying to solve for displacements, velocities, and accelerations given the sort of the mass contribution and the damping contribution to the system. So that's kind of what we're used to. This is, you mightn't have seen this before in this form. So given that form, at each step we're trying to solve for basically for a new lambda. Okay? Load control, it's really simple. All it does, well, the lambda at the next at the next step is equals to the current step plus my delta lambda. Okay? So the command is integrate a load control delta lambda. So when we're doing the lambda 0.1, 0.2, when the load control was 0.1, it just increments lambda by 0.1 at every time step. So that's load control. So that's the simplest one. A little more complicated is displacement control. What we're trying to do in displacement control is control how the degree of freedom at a node, how that displacement is going to change at every time step. We don't care what's going to happen to the load. Oh, so what we're trying to do is make, this is the constraint we're trying to enforce. That the displacement at this node at the next time step is equal to the previous one plus some delta u. So the command is integrator displacement control node. DOF corresponds to this, to the J. So what degree of freedom at a node we're trying to control. And then the delta u is just what is that increment. And so what opensees is trying to do is internally try and determine what is the delta lambda that is going to meet this, that is going to meet that constraint. Okay? So internally it's doing lots of stuff to figure out what the delta lambda should be based on the current state to give me that change in displacement I'm looking for. So this is kind of nice and small problems. You're able to control one. But the problem is when you get into large systems, it's kind of it's a little bit messy. You know, one displacement might be controlling things, and you might be missing out things in other parts of the structure. So then we start switching what's called the arc length method. So the arc length method, this is the constraint matrix we're trying to enforce at every time step. So the change in the displacements plus some alpha squared change in the load factor is equal to what's called the arc length, the delta S squared. So that is the constraint matrix we're trying to enforce at every single step. Okay? So from one converged step to the next, this is the constraint we're trying to enforce. So what opensees is looking for is what is the delta lambda that's going to cause this constraint equation to be true. Okay? Now most people sort of don't worry about this. The displacement control method and the load control method are the two most commonly used integration schemes in opensees. I'm just making you aware that the arc length exists. And these I swiped from Professor Philippou. So here's displacement control. We saw this morning. If this is our sort of load and sort of displacement characteristics for the model, load control will get us up to here. But we cannot reach this point here because there's basically we can't get to that point. The load response doesn't get up to that high. So this is what load control does. Displacement control, we've got constant increments in the delta U. We're just marching along, figuring out what the load factor is to give us these delta U's. And what arc length does is if this was our system, displacement control would basically go along here, and then it would pop over here somewhere. If we were doing displacement control would actually miss these little points in here. Okay? If it could find the solution, you're not guaranteed when you start going that far off the solution path, it's going to find the solution. So the arc length is the only method that will actually get to, be able to follow this curve here. As I say, displacement control will go from here to probably over here and along if we can reach this point. So there's basically visually the differences between the three methods. Okay? And as I say, typically we don't have systems that that look like this. So typically what we do in our earthquake engineering, we're doing transient integration schemes. In openseas, there's two types. We have our explicit methods, and we have our implicit methods. The explicit methods, if you look at the equation, they just depend on everything that's happened at the previous time step. Okay? The different options we have are central difference, Newmark explicit, and HXT explicit. All of these explicit algorithms need you to specify a linear solution algorithm. Okay? Do not specify Newton-Raphson if you're using central difference. It will not work. They have to converge in one step. They don't want to do any iterations. Hopefully the code, they'll spit out an error saying, this is garbage, this should not have been called twice. Update should not have been called twice. You should get some sort of message saying that this was an error. If you tried to use one of these with, say, Newton-Raphson. And then in the absence of damping, all these require a positive definite stiffness matrix. The mass matrix for our structures, typically, from the structural boys, we'll leave out those rotational masses. The implicit methods don't care if those rotational masses are there or not. For a structural system, if we're using one of these methods, we have to put in something for those rotational masses, because all these methods require AX equals B be solved, and all that A in all those methods is just the mass matrix. Okay, so that AX equals B, the A is just the mass matrix, and if the mass matrix is not a full system, it's not solvable, the analysis will fail. Everybody understand that? Okay. The other options are the implicit methods. We have all the standard ones, Newmark, HHT, and what's called the TRB-DF2. That's a new method. I'll talk a little bit about it. So the thing to know about when you use integration schemes, it's something everybody talks about, is how stable is it? Okay? Basically, are you going to converge, and how accurate is the solution going to be? And everywhere if you go to a textbook and look at what's the stability criteria for these integration schemes, they're all based on linear elastic systems. Okay? They only apply to linear systems. We're using them. Everybody uses them in nonlinear systems. Those stability, these things have been proven for elastic systems. They do not work. The same things do not work when you go to nonlinear. So a conditionally stable one means that it's basically bounded solution if the time step is smaller than a certain time step. And unconditionally stable is kind of the methods we like, in that we can use any time step, and we're going to, for an elastic system, we're going to have a stable solution, i.e. the solution is not going to grow. So for the common integrators in openseas, the ones most people tend to use, central difference or Newmark, these are the stability limits. If we're using central difference, it's got to be less than this. If we're using Newmark, the delta t over the period, it's got to be less than this. The thing about Newmark, the typical two Newmark methods, the average acceleration and the linear acceleration. Average acceleration passes the stability limit, so it's unconditionally stable if gamma and beta are specified as those two values. Linear acceleration method does not meet stability requirement, but it's conditionally stable. Linear acceleration is conditionally stable if this criteria is met. Now remember, when we're dealing with large systems, this Tn is not the fundamental period of your structure. It's the, you have to start looking at what are the other periods in the structure that actually start making an impact on what the response of your structure is going to be. And remember, in a nonlinear system, it's not that initial stiffness period you have to worry about. It's sort of further on down the line when the system starts going nonlinear. What is that period? They're the periods you have to worry about. And I'll give you some little examples, sort of showing you what picking the different periods can be, the different time steps. So again, I'm just swiping examples straight out of Professor Chopra's book, Dynamics of Structures. So this is the system. So here are results. Basically, so this is my delta T over Tn. Basically the theoretical results, central difference, Newmark linear, and Newmark average. As you see, the central difference has a problem. This is what we mean that it's not stable. Central difference has a problem if the delta T over Tn is too big. And you notice kind of what's going on with the other two systems. If we make it smaller, the delta T over Tn, same model, we just change the delta T over Tn. This is the solution we get. Again, the theoretical and the other two. You notice the fundamental period is slightly, these Newmark methods, they're shifting a little bit the periods of our structure. Again, the solution. And finally, if we make it small enough, delta T over Tn, small enough, basically everything, they all match. Okay? Now typically when you pick your delta T for your analysis, most people just figure out delta T that's coming from the earthquake. They're going to use that same delta T when they do their analysis. You might want to start thinking about what is the appropriate delta T, or what delta T should I use given my structure. You might not want to just pick delta T coming straight from the earthquake. Run a couple of things and just see what the impact is on the output. So as I say, large models contain a large number of periods. Typically, we select something that's unconditionally stable. Mohammed, you're going to enlighten us on something? Yeah, they're given by the stability limits. These things here. So if the delta T is over Tn is small enough, these things are unconditionally stable. No, in opensees you specify delta T in the analysis. I don't know what the period. I don't ask the structure for all the different periods. I don't know what periods you're worried about.
How do you make the decision?
Well, that's the modeling thing, right? Again, as I say, most people just take the delta T from the earthquake and they run it through it, and that's it. Right? They don't think about, well, what are the periods in my structure? What impact might they be? And because they get answers at the end, they're done. Right? Question? Hold on. Reagan.
You mentioned that the stability criteria mentioned that only for elastic structures. But
Yes.
then, say for instance you have a SDOF nonlinear structure, and at the most period will elongate post yielding. So if the criterion is satisfied with the elastic ranges, isn't it automatically satisfied with nonlinear as well?
No, it goes the wrong way on us. It's getting, because we're getting the higher frequencies start having an impact. Laura?
If I choose a delta T that's longer than the delta T for my ground motion, does it automatically take every other point?
It will take it right, and right now all it does is some linear interpolation. If it's not on the 2 points, it'll do linear interpolation between the two. I need something better in there. If you have a graduate student who's interested, we could do some, go back a couple of points, throw a little polynomial through there or something. I'd like something better. I just haven't had time to go back and do it. So nonlinear systems. Typically, we're worried about stability. Accuracy, we haven't a clue. Like we'll say Newmark is second, for elastic system, the Newmark average is second order accurate. Nonlinear systems, that is not the case. All we want to make sure is our problem just doesn't go berserk. We like it to be stable. As I say, the algorithms that are stable are not necessarily stable when we go to nonlinear. When we get to nonlinear system, this is what's required. We want to basically conserve total energy in our system. We want to make sure the change in the strain energy and the kinetic energy are less than less than or equal to the load coming in. So there are recognized 3 ways of doing this. One is to numerical dissipation. and the other is to enforce the conservation of energy. These two types of algorithms, none of them are yet in opensees. So if anybody's graduate student is looking to implement something, these aren't trivial, by the way. Most of the ones I've looked at, or everyone I've looked at so far, has required a lot of work at the element level to do stuff, to actually enforce these things. It can't be done basically at a higher level. But if there's somebody interested in exploring that, I'd be happy to help. So you might think, well, just cut delta t. We'll just go with a much smaller delta t. That always doesn't work. For those linear cases, it works. But when you go, because our thing is nonlinear, an example like this, we just, if we start cutting delta t, we just might start flip-flopping in our solution algorithm with regular Newton between two states here. So we don't get convergence. We don't get past our solution. So cutting the time step doesn't always work. And also, if the solution is explicit, even though we go to a really small time step, the new energy that's coming in might be so big as to still cause problems to our system. So we look at some dissipation algorithms. They were developed for large systems. We're only really typically, we cared about the lower modes of the structure. If you do sort of the modal analysis of a structure, all you really care about is the first couple of modes. You don't care what's happening to the other modes. So what these algorithms were introduced to elastic analysis was basically to dissipate those higher modes. And people have been now using them to dissipate these, sort of the energy that's coming in for these nonlinear systems. Examples of these integrators, basically the Newmark family of integrators. When gamma is greater than 0.5, the algorithm dissipates energy. The other two algorithms are HHT and the TRB-DF2. So here's an example. I forget what this was. It's the same model. So basically, I'm just using the different algorithms: HHT 0.9, 0.6, TRB, and the Newmark with the gamma is equal to 0.6, and the alpha was chosen for that stability condition. So you see, even with a really small delta t over Tn, that Newmark can damp out the response pretty quickly. Now if we set delta t over Tn to be larger, we see Newmark, again, it goes a lot faster. And then based on the HHT algorithm, what factor we put in, we can start seeing the damping, how quickly it damps. And then finally, if we pick it even larger. But again, the things to note, again, we're getting a little shift in our periods when we start using these dissipation algorithms. Like the Newmark, the theoreticals here, we're getting it starts shifting the periods a little bit. May have an impact on what the structures can happen to the structure. It's something you have to think about when you're doing this kind of stuff. So here's the same example, same algorithms. This is just a harmonic wave being thrown at the structure. The same delta t over Tn's. I guess you'll notice that the Newmark just damps out quicker. So when you're looking at these algorithms to dissipate the energy, it's not just the factors you specify for the integrator that's important. You also have to consider the delta t. As those examples show, the delta t is just as important as the factors you pick. The delta t over Tn. So you have to consider what modes we're going to play with, what we want to do, where we want to start dissipating our energy, and then you have to start picking the delta t based on that. So it really involves a lot more thought than you've probably thought you ever had to think about when you're doing this stuff. I apologize for that, but that's the way it is. As I say, most times people don't think about this at all, but it's something you have to really think about when you're doing these nonlinear analysis. Nonlinear dynamic analysis is not trivial. We've made it seem trivial in the other analysis, like if abacus or something, it makes it seem trivial, but it's really not. And it really requires a lot more thought than you probably care to give it, but you really must. And I encourage you to think about it when you're doing it, particularly the graduate students where you have all this time to play with different things. So here's an example. This is a real-life example. I could not release the source code. This example from Rutherford and Chikeen. They're looking at a base-isolated building. So basically, we got a friction bearing down at the bottom. It's kind of hitting the wall. When it was hitting the wall, they're having problems converging. The reason is our periods are jumping all over the place in the model. This is the initial period after gravity. This is just at impact. You see the big change in the periods, and this is when it's done. For dt at 0.001, the Newmark average acceleration and HHT, they both failed. They weren't able to get this through with sort of the other solution algorithms. So what they did is let's just throw on some dissipate. Let's dissipate some of these mode stuff, and all these HHT with 0.6, the TRBDF2 and the Newmark, all those integration schemes worked. They didn't have to go to other tricks like trying to cut down the time step to achieve convergence. And as you see, all the methods gave similar maximum displacements. So this is kind of like similar to contact. If you've got a problem with contact, you might have to start looking at these energy dissipation. The other option for energy dissipation is Rayleigh damping. You can look at that as well. But the Rayleigh damping wasn't working in this model either. So once we've constructed our integrators and everything else, as I say, this is our analysis static or transient, and then we issue the analyze command. And if you ever look at these classes in opensees, the static analysis and the transient analysis, these 4 lines of code is basically all that's there for a static analysis. Okay? So because we've gone for this really modular design and we've kind of divvied up things, this is a static analysis. You see, it doesn't care what the integrator is. It just says, invoke new step on the integrator, tell the algorithm to solve the current step, and then tell the model once we're done to commit. Okay? So that's how simple a static analysis can be if you start delegating stuff to the different components. Transient analysis is, it's basically identical, except the new step, the integrator, is just getting that delta t. And then other types of analysis, we can give you the eigenvalues, basically num modes. The general is not needed, and it will solve that problem right there. So then once we're done, we just issue the analyze command. So we saw this morning. So there is a static analysis with load control. Now that you've seen all these things, you know what all of these mean. Okay? So internally, this is what happens. We've got a static analysis that's composed of our transformation, our reverse cutting wiki, norm displacement increment, Newton load control, and our Banja general. That's internally what's happened when we've issued all these commands. Same thing with the dynamic analysis. You saw that again this morning. Internally, that's what happened. And we've pretty much gone through what all these different commands meant. So the thing to remember about nonlinear analysis, it does not always converge. Okay? The first thing we do, as I told you previously, is we check our model. We don't come running to Frank saying that opensees doesn't work. When opensees started, you would not believe the amount of emails we would get saying that your program doesn't work because it's not converging. Typically, it is not my fault. It is the model. And you need to sit down and think about your model. Where could the problem be in your model before you start emailing us for help? We spend a lot of time going through people's models, and typically there's not enough boundary conditions specified, or the materials have been incorrectly defined, giving them negative stiffnesses, or the elements, for example, the continuum elements, the nodes are numbered the wrong way, okay? If your model fails at the first step, it means that there's something wrong with the model in your definition. Check the boundary conditions, materials, and elements, okay? If you get a segmentation fault or something, that's my problem. Model problem, your problem. Segmentation problem, me. Okay, so what happens when the analysis fails? Okay, I've showed pretty simple analysis scripts. The nice thing about opensees is we can use these additional commands that Vesna was talking about earlier to actually do stuff in our scripts to get past the problem points. Okay, so I'm going to use these 3 commands that Vesna was talking about earlier. The analyze command actually returns a value. It returns a 0 if it worked. It returns another number if it fails. Okay? You're going to use that fact in our scripts to do something if the analysis fails. The get time command returns the current time in the domain. Okay? That when I was over here, whatever that t that was in the domain, that's what get time returns. And finally, the node disp command returns the current displacement at a node at a particular degree of freedom direction. Or we could use the node acceleration or the node velocity. We can use other commands there too. So here is basically we're doing displacement control and it fails. So what we want to do here is we want to do something in case that it's going to fail. Okay? So right up until here you've seen all this stuff before. Okay? So all I'm going to do differently now, instead of analyze 20 or analyze 100, we're going to put the analyze inside a loop. Okay? So basically, while some variable OK is equals to 0, so while everything's working, and while my current displacement is less than max u being our target displacement, we're going to go into this loop and do something. Okay, the first thing I'm going to do is I'm going to go do one analysis step, analyze 1. If that worked, I'm done. If it doesn't work, I have to go into my script. Okay, I go into my script and I'm going to change my solution algorithm from regular Newton. I'm going to change it to modified Newton with initial stiffness iterations. If I go to modified Newton with initial stiffness iterations, as I showed previously, even for a nice smooth curve, it takes an awful lot more iterations to converge. So here I got to bump up the number of iterations from 6 to 1,000. Now how many iterations are needed really depends on your model. So you see this little 1 at the end of the convergence test? That tells opensees at every convergence step, spit out the criteria, spit out what the current norm is. While it'll mean a lot of crap going to your screen, you'll also see that, if I'd maybe given it 2,000 iterations, it might have converged because I'm converging, but I'm not there where I want to be yet. So you might have, so this 1, you'll see when from this 1 whether this is working, or if you need to up this to 2,000, 5,000, 10,000. Okay? I typically stay in the 5,000 range, 10,000 range. I've never tried anywhere where it needed 100,000 iterations to get there. But then I haven't dealt with models, over 100,000 degrees of freedom. When you get to really, really large models, this number here might need to be really, really large. So after we've done this, we've changed our solution algorithm, we go do another analyze 1. And then when we're done with the analyze, we want to set our algorithm back to doing regular Newton. Modified Newton is slow. We want to go back to regular Newton, and we want to go back to our 6 iterations. We don't want to be doing 1,000 iterations. So that's all this script is doing. And then right at the bottom, we're going to get our current displacement. So we can go back when we come back here, is the current, have we reached our target yet? So does everybody understand this little while loop? Every nonlinear analysis script you write will probably have a while loop that's based on this. Okay? Now they can get a lot more complicated, and my good friends at Stanford can come up with have some of the most complicated analysis scripts you've ever seen. I've seen from certain scripts there's like 20 if statements inside their do loop. Okay? Now somebody at Stanford at some point has got to go back into these scripts to see if these things make sense. Seriously, because they're just spending, all the students are using them, and they just take so much time. And there's a lot of stuff that's in there that tests that could probably get them thrown out. So just run them, see if they work. Because a lot of these things is like they fail every single step for every single model that I've ever looked at. So what's the point of keeping them in there? But it'll just save the students a lot of time.
And then again, would you suggest doing the analysis step by step like this, although it takes a lot more time?
Well, okay. The time is really spent in in solving that AX equals B matrix and figuring out what the mapping is for the equation solver. So as long as we don't change the equation solver, that the time is not going to be spent there in this part. And all the time is going to be spent in the analysis anyway. So the little bit of crap that goes on while we change all these algorithms doesn't really affect the performance, okay? Especially if these things are taking, hours to run or minutes to run. The stuff that's going on in the script is not going to impact. We could also have done, outside here, we could have done analyze 10,000 outside here, right? And then if it failed, then we come back in wherever we are, we start doing the analysis.
Is that possible?
Oh, yeah. Yeah. As I say, that's just set OK, analyze 1 is just, set OK, analyze whatever, max U over delta U is. So we try all those iterations. Only if that failed do we come inside this while loop, right? That's all it is. In fact, next time I might even put that up on the slide. That's how simple it is. So for the transient analysis, we can do the exact same thing. The only difference, instead of nodal displacement, we're looking at the current time. And instead of our target displacement, we're checking that the current time is less than our final time. That's the only difference between the static and the transient. Right? And it makes sense. And from a scripting point of view, you see how powerful this can be. If your analysis fails, let's do something. If the analysis fails, you might actually think of, well, let's write to a file that, hey, we had problems at this time step. When I'm done, go look at the results, after this time step. Do they make sense? Okay? There's lots of things you can do when this thing fails. And there's things you should be maybe putting to the output to remind yourselves that, hey, we had problems here. Let me go have a look at what the solution is, if there's a big kink in my solution thing or something going on at that point. Maybe the results after this point are totally meaningless. Up to this point, the results are fine, but after this, when I'm having to turn off, you can turn off convergence for a step or two if you want in opensees. So after you turn off convergence or you go to one of these initial iterations, maybe I've just gone on the wrong solution path and I'm, instead of going to San Francisco, I'm going through Oakland or somewhere like that. Okay? So if it's still not working, and you've tried all the changes to the script, then we start looking at the message board, and we start posting our problems to the message board. But remember again, the first thing we do before we post is we search, right? Search the message board, then we post our question. And only if we have a segmentation fault. The program suddenly dies and says it wants to debug. Or do you want to debug the program pops up to the screen. Do you send me an email? Okay? So that's the only time you're allowed to send me a direct email, unless you're a professor, of course, is if you get a segmentation fault. Otherwise, the program works just fine. There's something wrong with your input. Okay? So either figure it out yourselves or post a question on the message board. And I suppose if I don't respond or Vesna doesn't respond, quickly enough, give us a couple of days, then you can start sending Vesna an email, and after Vesna you can try me. I have to put Vesna's email message up here next time. Any other? Okay. I don't really need to. So here's basically a model. Vesna's going to go over this tomorrow for the nonlinear case. So the question about the feet, the units. So here's a little thing where I'm setting my feet to be 12, my inches to be 1, and my centimeters to be this. So I'm setting the width to be expression 42 times feet. So that's kind of how you could sort of play with units if you wanted to. As I say, opensees itself is unitless, but you can introduce units in the script if you want. As you see, I stopped using it for the rest of the stuff. Unioxide materials, I'm going to create a reinforced concrete section. Vesna's going to talk about that tomorrow. I'm not going to talk too much about this. So that's the gravity load analysis of that frame. Those commands were in the file rcframe.tickle. So if we want to do a gravity load analysis of this frame, we source in rcframe.tickle. We create our load pattern, create our analysis object, perform the analyze. And then we want to do transient analysis with load control. The only thing I will mention is that at the end of gravity analysis, what I'm going to do is I'm going to set those gravity loads to be constant. You don't have to put those gravity loads inside a constant load pattern. You can have them varying up as much as you want up to a certain point. And then when you issue the load const command, that will cause every load pattern from that point on to remain at that. Basically, the load factor doesn't change any point after that. So from then on, every load pattern that exists before that command is basically freezes. They don't change the load factors. And then the command is this is an option to reset the time in the domain back to 0.0. Basically, so you don't miss the first couple of points in the earthquake excitation. And pretty much all these other commands we've seen in some of the other examples I gave. The only thing I'm doing here is I'm wiping analysis. At the end of my gravity analysis, it's a static analysis. I want to throw it away. The way you throw an analysis away is the wipe analysis command. There's no space after the E. If you put a space after the E, your entire model will disappear. Okay? But everything else you've seen before. So here are the results when you run it. As I say, MATLAB is a great, useful little tool for plotting the thing. So what I'm doing here is I'm doing the same example. I'm just showing how to do multi-support excitation. So the difference are in red to what was on the previous slide. So instead of a uniform excitation pattern, the pattern is multi-support. The multi-support command, you specify a number of different ground motions. In this example, basically, I'm going to use the same ground motion at the supports. I could specify different ground motion at each support if I wanted to, just by issuing multiple different ground motions. And then to impose a single point constraint inside the load pattern for that ground motion, I'm going to use the impose motion command. It takes the tag, the node number, the degree of freedom that ground motion is going to act, and whatever the ground motion tag is itself. So here I'm at nodes 1 and 2. I'm going to impose ground motion 5 in the 1 degree of freedom direction. And the only other thing I had to do is in that previous gravity analysis, the two nodes 1 and 2, are both currently fixed in the x direction. So we have to go in and basically remove them. So here I am removing the constraint from node 1 in degree of freedom one direction. So that basically takes that constraint out. That's in the model, previous model. So then I go run this, and this is my multi-support excitation. And here's the results when I compare the two. And Vesna was talking about why the difference exists. Which one of my Stanford students wants to tell me? Reagan was the guy. Reagan, you have to tell me why these are different. Right, exactly. So the multi-support is the absolute displacement. The uniform excitation is relative. If you then come back in and add in the ground displacement to the uniform excitation, the two will be on top of each other. So remember, when you're doing uniform excitation, the results are always relative. Whether it's opensees, Abacus, Adena, whatever the program is, if you're doing a uniform excitation, the results are relative. So if you want to see what's happening, the accelerations of some equipment, you don't want the relative, you want the absolute. So sometimes you have to come back in and add in those, the actual terms to get the absolute values. Any questions? So I'm going to finish there.